on a problem with you. This one is actually from page 101 in your textbook. It's question number 1, and questions number 2 and 3, I think, are part of your book homework. So hopefully this will give you a little bit of perspective. So bells are ringing. All right. So it says that measurements made in 1910 indicate that the common flea is an impressive jumper given its size. For example, if the flea's initial speed is 2.2 meters per second and it leaps at an angle of 21 degrees with respect to the horizontal, and the jump lasts 0.16 seconds, what is the magnitude of the flea's horizontal displacement? All right, so I'm going to start by just kind of figuring out what we know. So it says that the initial velocity is 2.2 meters per second at an angle of 21 degrees. And then it says, oh, it also gives us the time, which is kind of an interesting thing to know. It says the jump lasts 0.16 seconds. What is the magnitude of the horizontal displacement? So that's one of our questions. I'm just going to make a note here. So horizontal displacement is going to be delta x. And it says, how high does the flea jump? So this one's a little bit interesting, but we will take a look at this. So I'm going to say, we're going to call this delta y maximum, which is a little bit different than the delta y that I had in the last video. So generally, I like to start with a picture. So let's go ahead and draw ourselves a little picture. So here is the ground or the table or whatever that flea is on, the dog's back perhaps, okay? And it's going to launch at an angle, go up, and come back down. I'm going to draw that initial velocity vector, and we'll make it like this. I'm going to draw it up like this. So it's going to be a straight line. This is the velocity that the flea starts out at, and it has an angle, it says, of 21 degrees. So this is 2.2 meters per second. Okay. So then, just like for every other projectile motion problem, we're going to set up our patented givens chart. So we've got delta x, we've got v initial in the x direction, and the acceleration in the x direction. I'm just going to leave those blank for just a moment. We've got delta y, vi y, and ay, okay? And then the thing, of course, that pulls it all together is time. I'm going to go ahead and fill in what I do know. So they asked what the horizontal displacement is, so I'm going to go ahead and put a question mark there. We, in just a moment, will calculate these initial velocities. So we're going to hold tight on that for just a second. I do know, because it's always going to be true in these problems, that the acceleration in the x direction is 0 meters per second squared. That looks a little bit like a 6. I don't want to confuse you. Okay. And we also know that the acceleration in the y direction is negative 9.8 meters per second squared. They told us that the time was 0.16 seconds. Okay. And then the delta y, this is where it gets a little bit funny, and I just want to make this really clear, okay, that the delta y for the picture that I've drawn, when it goes up and comes back down, the delta y is going to be 0 meters. But I'm also going to write over here one more little column, and that's going to be delta y max. That was one of the questions they asked. And I'm just going to think about it for a moment here and think about at the y max, let's think about where that exists. Does it make sense that that's going to exist at the very, very top? Delta y max will exist here. And at the very top of this flea's jump, in the y direction, it goes up and comes back down. And at that very top moment, does it have any velocity in the y direction? Think about it, think about it. It goes up and comes back down, so it has a velocity that's positive and a velocity that's negative on the way down. And at that very top moment, I'm going to say that the velocity, the y velocity at that maximum height, I'm going to say Vy at max is equal to 0 meters per second. Hopefully that makes sense to you. So it's going to go up and it's going to come back down, and right at that top spot, it's got 0 velocity just for a moment, okay? So I've added another column to my givens chart. So hopefully those make sense so far. Now, there are 2 questions that it's asked us, right? The first one asks about delta x, and in order to do that, we need to know the initial velocity in the x direction. So I'm going to draw my little vector, but I'm going to draw it really big so that I can see it better. So this is my initial velocity vector, okay? The initial velocity was 2.2 meters per second, okay? And I'm going to break that down into an x piece. This is VIX, okay? And a y piece, VIY, okay? And here is that angle of 21 degrees. So just like I did with my vector components earlier, we're going to break the initial velocity into an x and a y. So let's go ahead and do that. Let's start with the x. So I'm going to walk through this kind of slowly because I want to make sure you see it and you get it. This is the adjacent side, and I know the hypotenuse, so that means I'm going to use not sine, I'm going to use cosine. Got ahead of myself there. Cosine of theta is equal to adjacent over hypotenuse. So that means that the cosine of 21 degrees is equal to VIX over 2.2 meters per second. Okay, and you're going to pull your calculator out. I'm going to pull mine out as well. And I'm going to do 2.2 times the cosine of 21, and I get a value in the x direction of 2.05 meters per second. That is my initial velocity in the x direction, 2.05 meters per second. Similarly, I can do the same kind of thing with the y. So the y is the opposite side. So we're going to use sine. The sine of theta is equal to the opposite over the hypotenuse, okay, which means that the sine of 21 degrees is equal to VIY, that's the thing we want to know, divided by 2.2 meters per second. I want you to do this on your calculator as well. And if you get stuck, if you need help, then let me know, okay? So we're going to do 2.2 times the sine of 21 degrees and find out that the velocity in the y direction is very small, which makes sense because that 21 degree angle is really small. So we've got 0.79 meters per second. I'm just going to round that to the nearest hundredth for simplicity here. So 0.79 meters per second. Okay, so now I can solve the first part of this problem by using all of the x stuff and my time. Okay, so I've got my x, I've got all of the pieces and time, and we're going to go ahead and do the same thing that we've done every other time that we've done these problems. I'm going to move this down here so we've got some space. Get rid of this picture. Here we go. Okay, so we're going to say delta x is equal to VIX, little x, times time plus 1/2 AX t squared. We look back up here and remind ourselves that the acceleration is 0. So we've got delta x is just VIX times time. We know the initial velocity and we know the time, so we can plug those things in. We can get delta x is equal to 2.05 meters per second times 0.16 seconds. Plug it into your calculator as well. Play with me, it's more fun. 2.05 times 0.16. I'm getting a displacement in the x direction of 0.328 meters. Now that might seem really small, but again, let's think about this. A flea, and if you convert that, that's really, you don't have to do this, but it's just kind of for perspective, that's 32.8 centimeters. That's more than a foot. It's jumping pretty far. That's kind of cool. All right, so that's the first half. The second half, they want to know how high does the flea jump? So I'm going to come over here and look at what I know. I know this time, but the trick about this time is that that's the time for the whole jump. Here's what I'm thinking, is that we know, let's see, what do we know? We know, or we want to know, the displacement. We know the initial velocity. We know the final velocity, okay? And we know the acceleration. And I think if I look at an equation sheet, I can find something with those 4 things in it. So you take a look at your equation sheet. I'm going to take a look at my equation sheet and see if we can find an equation that's got those 4 things in it. This is like my final velocity at the very top of the jump. And I know that V final squared is equal to V initial squared plus 2A delta Y. Everybody see that equation? We're going to do some solving. We can find things that equal to 0, like the final velocity, and we can say vi squared is equal, or negative vi squared, I suppose, is equal to 2a delta y. This is the y max that we're looking for, okay? So vi squared over 2a is equal to delta y. I'm going to plug it in. You should too. So we've got 0.79 meters per second. We're going to square that. Oops, I dropped my negative sign. Sorry about that. Divided by 2 times negative 9.8 meters per second squared. Okay, so the only one you actually square is the velocity, right? So we're going to do 0.79 squared divided by 2 times 9.8. I put my negatives in there but forgot to say them out loud. Okay, and that gives me an answer for delta y max, the maximum height, of 0.032. I went out one extra decimal there, if that's okay, meters. And again, just kind of for perspective, that means that the flea is jumping up 3.2 centimeters. All right, so there you go. Hopefully that will help as you go through more problems.